In this video, we're going to learn about stoichiometry, and this is just simple introduction to what stoichiometry is, how our balanced chemical equation will relate reactants and products in terms of moles and grams, and we'll also learn how to switch between products and reactants. And let's start with stoichiometric calculations. Our stoichiometric calculations are based off of dimensional analysis. So if you can set up a dimensional analysis problem, you really can apply stoichiometric relationships for anything. Like, for example, we have here this example of how to make 12 pancakes. So this is a recipe for 12 pancakes. Now the recipe calls for 2 cups of pancake mix, 1 cup of milk, and then 4 eggs. Okay, and on the first slide here, it asks how many eggs are required to make 24 pancakes. So I can say that if 4 eggs can be in a recipe of 12 pancakes, all right, times, now we want to transform it to the 24 pancakes we have here. Okay, so pancakes will go with the pancakes, and we get a total of 8 eggs. Okay, same thing can apply to the cups of pancake mix. So if we have 2 cups of pancake mix, and this will make 12 pancakes, all right, times the 24 pancakes will give me 4 cups, because the pancakes will cancel the pancakes, will give me 4 cups of pancake mix. And lastly, to show you that also can apply to the milk, okay, so the recipe calls for 1 cup of milk for 12 pancakes times the 24 pancakes equals to 2 cups of milk. So using this relationship, we can actually adjust our recipe accordingly to make as many pancakes as we want. So how does this now relate to our chemical reactions? We can use our balanced chemical equations, specifically the coefficients, what will provide us with how many molecules, okay, if it's a covalent compound, or formula units if an ionic compound, in the reaction, and the relative amount of moles of both reactants and products. So this will be for reactants and products. Okay, so looking at this chemical reaction over here, we have 2 moles of hydrogen gas reacting with 1 mole of gaseous oxygen to give me 2 moles of liquid water. So in other terms, I can say that 2 molecules of hydrogen can react with 1 molecule of oxygen to give me 2 molecules of water. Okay, and if I want to now translate this into moles, I can say that 2 stoichiometric moles from the balance equation of hydrogen can react with 1 mole of oxygen to give me 2 moles of water. And now we can use this mole to mole relationship using the coefficients in the equation along with masses to actually, along with the molar masses to convert to actual grams that are measurable in the lab to perform my chemical reactions. Now, By definition, stoichiometry is the numerical relationship between amounts of reactants and products in a balanced equation. So if we look right here at this flow chart, we can see on the left here in green are the masses of the substances, which I can convert the moles using here molar masses. And then we will do this in class, is how to find a limiting reactant, okay, and find its moles. And then using the balanced chemical equation, we can also convert and the mole to mole ratio, as I showed you on the previous slide, to determine the moles and the masses of the products. And vice versa. We will go through this very thoroughly in class and in this video. Now, let's start to apply the stoichiometric calculations to our example right here. And you can actually do the calculation in multiple ways. And I'll show you the two methods. The two methods should give you the same answer, but pick and choose. There isn't a right or wrong thing. So in this example, it says how many moles of oxygen. So we want to find the moles of oxygen that can be produced by the decomposition of 32.8 grams of potassium chlorate. And in this case, I want to go to the next slide to show you the first method. So here I'm starting with 32.8 grams of KClO3, and this is here my reactant. Okay, and I want to find the moles of oxygen, which is my product. Okay, so in this case, I will start with the 32.8 grams of potassium chlorate. Okay, and I note that you are responsible for the number of sig figs right here. So in this case, I have here the lowest number of sig figs, and my calculation is going to be 3 sig figs right here. The second step is I want to now convert the mass of the potassium chlorate to moles, and this will be using the molar mass. So this is the molar mass of potassium chlorate. And so in every mole of KClO3, I have 122.55 grams of KClO3. And then to convert now from the moles of KClO3 to oxygen, I'm going to use the mole to mole relationship here between oxygen and KClO3. So for every 3 moles of oxygen produced, I have 2 moles of KClO3 consumed. Okay, and finally, I can see here that I ended up with moles of oxygen. Now again, since the lowest number of sig figs are 3, I highlighted here, so it should be 0.401 moles of oxygen produced. Another thing you want to note, this applies to any dimension analysis calculation, that if you want to end up with whatever you're asked to determine in the question, it should always be on top. Like, for example, it asks me for the moles of oxygen. So everything, again, should cross out. So grams of KClO3, moles of KClO3, and finally, I ended up with the moles of oxygen. Now, the second method is called the amount stable method. And this one, you set up a table called the amount stable, where you are going to, on top here on each row, you are going to place the reactant and then the product over here. And on each row here to the very left, you're going to have the initial. The initial here represents the initial moles of each reactant or product. Of course, at the beginning of the reaction, since there are no products before the reaction starts, I only have the moles of the reactant itself. And you can see down here as where I demonstrated that I used the 32.8 grams of KClO3 and converted them to moles. And of course, since at the start of the reaction, there are no products at all, so I put here 0. Now, for the change represents how many moles are consumed and produced. So since reactants are consumed over the course of the reaction, we add a negative sign. And for products, we add a positive sign. And another thing to be mindful of is the stoichiometric coefficients. Now, if we here for KClO3, we will use the mole. So I said that it is negative 0.268 moles, which are consumed from the KClO3. Now, how about KCl? Since the mole to mole ratio is the same for KCl and KClO3, I'm going to add a positive because it's produced 0.268 moles. Now, for oxygen is different because now the mole to mole ratio is different. And like on the previous slide right here, I will set it up as for every 3 moles of oxygen produced, I have 2 moles of KClO3 consumed times the moles of 0.268 of KClO3 that I'm working with. Now the final is simply, we'll add up the initial plus change rows to give me the final. And of course, if you notice here, it's 0 at the end of the reaction for KClO3. For KCl, it's 0.268 and 0.402, which is nearly the same exact answer as I got from here. Okay, so whatever method you want to use, please feel free to use it. I think the first one is a simpler one, so you might want to stick with it. Now, let's check our understanding and see how we can apply. I'm using, again, the same example for the reaction, but if you notice, I'm going to be altering the problem in so many ways. So in this problem, it asks how many grams of KClO3 must decompose to produce 50 grams of oxygen. Now, since it wants to end with grams of KClO3, and it starts with 50 grams of oxygen. So I'm going to say that I have here 50.0 grams of oxygen, and I have here 3 sig figs times 1 mole of oxygen over, now the molar mass of oxygen is 32.00 grams of oxygen, okay, times, we have here, now we want to convert from moles of oxygen, so the moles of oxygen should be at the bottom, so I can say 3 moles of oxygen for every 2 moles of KClO3, okay? And finally, since it wants the mass in grams, I'm going to use the molar mass of KClO3. So I can say that 1 mole of KClO3, I have 122.55 grams of KClO3. Okay, and I'm going to check the number of moles. So this is the least number of moles that I have in my question. And I'm going to say here I have 127.65625 grams of KClO3 that must decompose using 50 grams of oxygen. And I'm going to highlight my sig figs right here. And the answer is nearly 128 grams KClO3. Now, let's work on another one. And I want you now to pause your video and try to do this on your own because it is almost the same as the one, and I want you to try it for yourself. And meanwhile, you are trying this for yourself, I'm going to read the question and work on it. How many grams of KCl, now potassium chloride, are formed when you have 28.3 grams of oxygen formed in the decomposition of KClO3? So in the last question here, I was relating reactants to products. You can also use this relationship to relate reactants and reactants. It's very flexible. It's very beautiful as long as you have your balanced chemical equation and you have the amounts in grams or moles of a reactant or a product, you can really do anything. So like I showed you before, it's if we have 23.8 grams of oxygen, and then we want to convert from moles of oxygen. So we're going to use the molar mass of oxygen, which is 32.00 grams oxygen. And then, so let's check here, grams are gone. Now we want to convert from moles of oxygen to moles of KCl. So I can say for every 3 moles of oxygen, I have 2 moles of KCl. And then finally, so moles are gone. And finally, I want to end up with grams. So grams of KCl on top and moles of KCl on bottom. So I have 74.55 grams, which is the molar mass of KCl. And double check, yes, moles are gone. And I have here 43.9534375 grams of KCl produced. Now, the least number of sig figs here is going to be for oxygen. So in this case, I can say that if I round this, it'll be 44.0 grams KCl.